On this page of notes, we have a very important analysis for you to understand. So please take your notes carefully, spend time pausing the video when I indicate for you to do that, and really understand it and ask questions should you have them. The Kirchhoff voltage loop is really a Kirchhoff voltage circuit analysis, and shortened to KVL. And I want you to know that fundamentally, this is based on conservation of charge and energy. So please make sure you get that into your notes. It is often a multiple choice concepts question if they're pulling multiple choice questions from test banks for this unit. So what are we doing? So anytime we have a circuit and we want to know everything about the circuit in terms of the voltage drops across all the elements, the currents running through the circuit, we are going to do this Kirchhoff voltage loop circuit analysis. So the first thing I would like you to do is pause the video, but get in all of these values into the circuit. So all of the 8, the 0.2, the 5, get all of those in. So pause the video and get all those values into your circuit. Okay, so hopefully you have those in. So let's see what's going on here. To understand the analysis, we have to understand what a junction is and what a branch is. A junction is any point in the circuit where the current can split into two different values. So like A here, current I1 can break into I2 going down and I3 going to the right. So for our analysis, we're just going to pick an I1 and let it break into I2 and I3, even if we've chosen the wrong directions. We'll see our answer at the end will let us know whether we chose correctly or not. Now, a branch of the circuit, on the other hand, is where the current can't go anywhere or split. So even though we have other elements, like I have this green I1 in here, this green I1, even though it's going through the battery here, and it's going through the resistor R1 here, it's going through the little internal resistance here, even though that's the case, it can't split, so that's a branch. Well, to start our analysis, we're going to just follow our rules for our analysis here. We're going to start at any junction. In this case, I picked A, and what I did was I said I have this green I1, and I just said, okay, I'm going to assume some of it goes down and some of it goes to the right, and once it goes to the right, then it stays. It goes to the right, it goes to the right, it keeps looping around, and it comes back here, and look, I have conservation of charge. My purple and my blue combine back together to make the green. Now, it is really important, so I don't have it highlighted, but I really should have it highlighted, that you want to make sure that you have this down here, that you must have n minus 1. So it's not just make, it's you must make n minus 1 junctions, equations, so that in this case we do only have one equation, because I have I1 coming into junction A, breaking into I2 and I3. Now, it's n minus 1 because if I went to B, it would be redundant. I would be generating a second equation, but not independent variables. So in terms of the mathematics, I didn't put it in here, but we really should put in a coefficient of 1, coefficient of 1, and a coefficient of 1. So just because the 1s are there, that doesn't mean the I1 value itself is 1. That's just the coefficient in front of the variable. Now, the conservation of energy part of our analysis comes from these Kirchhoff voltage loops. Now, a Kirchhoff voltage loop is fundamentally a theoretical construct, so it doesn't actually exist, but we put them into the circuit to allow us to do this conservation of energy statement. So this one is a conservation of charge statement. This one is a conservation of energy statement. And it says here that we need to draw as many of these theoretical construct, Kirchhoff voltage loops, as needed to encompass all of the elements in the circuit. I'm going to describe that by way of the example, or explain that by way of the example. Well, here we have sum of the voltage sources. Well, sum of the voltage sources for us means batteries. So in this case, my blue loop here. So that I made this my first loop. So if you want to compare your answers to mine, just mimic my loops for right now, and hopefully you'll see how they're made, and you can choose other ones in the future. So if I choose this as my first theoretical construct, I'm going to look at conservation of energy around that loop. I have some of the voltage sources. I have 2-volt batteries in that loop. Now, the plus and the minus come from whether the loop is coming out of the positive, plus, or going into the positive, negative. So that's what you'll do with your adding and subtracting batteries. Now, the sum of the voltage drops is based on Ohm's law, IR. And to get whether there's positive or negative in front of the IR, and here you can see they're all positive. We'll get the negatives for our green or red in a moment, is to look at whether my current direction and my loop direction go in the same direction through the element. If they go in the same direction through the element, it's a positive IR, and when we do the red, we'll see that sometimes the loop and the current go in opposite directions, and that's going to be a negative IR. Now, in terms of the language here where it says draw as many of these loops as is required to touch all the elements, notice my blue loop missed the R3. So the blue loop didn't touch the R3. That's why I have to add another red loop to touch the R3. Now, I could have chosen a perimeter loop, so I'm just going to put that in here quickly, dashing it. So I could have chosen this perimeter loop. That would have worked as well. But for right now, I chose my interior, and I chose clockwise. I could have chosen one clockwise, one counterclockwise. As long as we're consistent, that's fine. So what we have here for our red loop is sum of the voltage sources. We only have one voltage source, the 15-volt battery, and since my red Kirchhoff voltage loop is coming out of the battery, that's why it's positive. And as I said, I have the negative here because the current and the loop were drawn in such a way that they oppose each other. And then I have the positive and the negative here. So what we get are 3 equations, 1, 2, 3, and notice I put in zeros for completeness. So even if the loop doesn't go through that section, I will put in a 0 there because what I have now are 3 equations, 3 unknowns, and I'm going to plug them into a 3x4 matrix and row reduce echelon form them. So let's go to the next view. So same problem, and all I did was have took my 3 equations and made them into a 3x4 matrix. Now, when I made them into a 3x4 matrix, I had to be a little careful. I have 1I1, 1I2, 1I3. So I left the 1I1 alone. When I bring the I2 and the I3 over to the left, that's where my negatives came from, and then I have a 0 on the right. So you want to put them in the same form. You want to line up the I1s, the I2s, and the I3s to get the proper 3x4 matrix. Now, please take the time to do that. Plug it into your calculator and make sure that you get these as your answers. What's important about these as your answers is notice my I2 that the calculator provided me was actually negative. That negative means that I actually chose wrong when I chose I2 going down. So the I2 actually goes up so that I1 and I2 come together to make I3. And that kind of makes sense. This battery's pushing forward, this battery's pushing forward up, so they would come together. But my point was you didn't need to have that correct to get the correct answer. If we do our row reduced echelon form correctly, that negative here will show us whether we got our current directions correct. And typically when questions are asked, they're asking for the magnitudes of the current, but you certainly would be able to indicate the directions as well. So really important page of notes. Pause the notes, get everything in here that you need to get in, and ask questions, and we'll be doing examples as well.